Hi, welcome to my presentation entitled Surprising Gate Oscillations in Silicon Carbide Power Modules. My name is Yanfeng Shen, and I am a power electronics engineer with Danfoss Silicon Power R&D Munich. Here's the agenda of my presentation. First, I will introduce the gate oscillation issue by showing a failure example of silicon carbide power module caused by excessive gate oscillations. Then I will talk about the classification and the modeling of gate oscillations. After that, I will show you how to express these gate oscillations by design. Finally, I will summarize this presentation. As you know, silicon carbide MOSFETs offer a lot of advantages over silicon counterparts, such as high switching speed, lower and temperature-independent switching losses, lower reverse recovery charge. However, we're also facing many challenges if we want to make the most of silicon carbide MOSFETs, like the requirement of lower looping inductance and faster short-circuit protection. But today, what I'd like to discuss is the gate oxide sensitivity and gate oscillations. So, silicon carbide MOSFETs have a conventional gate oxide as silicon MOSFETs. However, the silicon and silicon dioxide interface is worse than silicon and silicon dioxide interface. Therefore, the gate oxide of silicon carbide MOSFETs is more sensitive to field stress, so we must limit the maximum gate source voltage. Otherwise, it will undermine the long-term gate reliability or even result in catastrophic failure. In the meanwhile, because of the lower capacitance and higher transconductance, it's more likely for silicon carbide MOSFETs to operate in unstable regions, particularly in switching and short-circuit conditions. So, due to the two facts, the higher gate oxide sensitivity and the higher proneness to instability, the excessive gate oscillation is identified as the killer of silicon carbide power modules. Here shows an example of silicon carbide power module failure during turn-on at 175 degrees C. The green trace is the measured gate source voltage. From the left-hand figure, we can see that the high-frequency gate oscillation is building up in the middle of the turn-on process. It is because this silicon carbide power module is operating in an unstable region there. When we further increased the drain source current, then this power module blew up as the gate voltage substantially exceeds the limit, which can be seen from the right-hand figure. Then, how can we express these high-frequency oscillations to avoid failure? Well, to answer this question, we need to get a better understanding of the oscillations, including the oscillation mode and mechanism. The two figures here show our identified two oscillation modes for the multi-chip parallel silicon carbide power modules. That is the common mode oscillation and the differential mode oscillation. We can see that in both modes, the gate oscillation loop couples with the power loop. Theoretically, the differential mode oscillation happens inside a power module, so in many cases, it may be not observable from external pins. So the differential mode oscillation actually is a hidden threat to the reliability of power modules. Also, compared with the common mode one, the loop inductance of differential mode oscillation is lower. So the differential mode oscillation usually causes a much higher gate voltage reading, resulting in degraded gate oxides or even catastrophic power module failure. After the mode classification, now let's move on to the flowchart of how we model these oscillations and how we optimize our silicon carbide power module design. Basically, with silicon carbide MOSFET chip parameters and power module package parameters, we can build the small signal models and transfer functions of different oscillation loops. Then we can use the damping ratio as an indicator of system stability. The higher the damping ratio, the faster the oscillations can be damped. If the damping ratio is negative, then it means the system is unstable and the oscillation won't be damped. Instead, the oscillation will be building up and may cause gate failure during switching. Then, how can we increase the damping ratio to improve the stability performance? Yes, we can optimize the chip parameters by screening and selecting the most suitable silicon carbide MOSFET chips. Fortunately, we are chip independent, and this flexibility provides us a significant freedom to choose the optimum chip for specific applications. Meanwhile, we can adjust the power module package parameters by optimizing chip layout and package design. In both ways, we are able to develop robust and reliable silicon carbide power modules. Now let's take a look at how module parameters affect the stability performance of silicon carbide power modules. One of the most important parameters is the internal gate resistance RG-int, which consists of the internal chip gate resistance RG chip and the substrate gate resistance RG sub, as shown in the figure at the bottom left. The figure on the right hand shows the damping ratio curves versus the gate source voltage at different internal gate resistances. As can be seen, by increasing the internal gate resistance, we can lift the damping ratio curve from the unstable region to the stable region. Then the gate oscillation can be well damped. The increase of the internal gate resistance RG-int is normally achieved by adding substrate gate resistors into power modules. However, these added substrate resistors substantially increase the volume and cost, slow down the switch speed, and result in higher switching losses. So, is it possible to operate in the stable region without adding any substrate resistors? Yes, the answer is to optimize the chip layout and package design. As the chip layout and package vary, the equivalent drain, source, and gate inductances of parallel chips will be changed accordingly. The two figures here show a stability comparison between a baseline power module design and an optimum design. The red curves represent the case with zero substrate resistance. We can see that the optimum design enables the silicon carbide power module to be always operating in the stable area, even without substrate resistors. So, from this comparison, we can clearly see that chip layout and package have a significant impact on the stability performance of silicon carbide power modules. So in this presentation, I have shown that excessive gate oscillation is a killer of silicon carbide power modules. Then I identified and modeled the common mode and differential mode gate oscillations. Finally, I showed you a parametric analysis to see how design parameters like the internal gate resistance, chip layout, and the package impact the stability performance and gate oscillations of silicon carbide power modules. Thank you for your attention.